Welcome to IB Chemistry exam preparation, exam tips for both standard level and higher level. Today, through our lesson, I'm going to focus on topic 6, kinetics, rate of reactions for standard level. I'm going to discuss for today section 6.1, which is about collision theory and rates of reaction. Through my lesson, I'm going through defining the rate of reaction. We will also cover different experimental methods can be used in order to monitor the rate of the reaction. Besides that, we will also learn how to calculate the rate of a chemical reaction taken from graphs. So let's get started. So the first thing that we need to answer is, what does the rate of reaction mean? Talking about the rate of reaction, definitely we are considering the speed of this chemical reaction. So if we want the speed, we are talking about the time. The speed of different chemical reactions varies hugely. Some chemical reactions are considered very fast, and others, they are actually very small in the rate. So they have a very slow rate. So the speed of the reaction, it can be described as the rate. Looking at the different figures presented inside the slide, we can find that we have here different types of chemical reactions: roasting, baking, explosion. Starting with the roasting, it is considered a slow chemical reaction, while baking, it's fast. And for the explosion, compared with baking and roasting, I can classify it into a very fast chemical reaction. The first thing that we need to learn is to know how to define the rate of the chemical reaction. Going through the definition, the rate is the change in the concentration of either reactants or products per unit of time. So if we go back another time to the definition, we're going to find that the concentration change, it is so essential. And number 2, we have also the time, which is also considered also very important. So if we want to go through the rate, we need to remember that it's the change in concentration per unit of time of the reaction. If I'm going now to start with the unit of the rate, since I have concentration and I have a time, so it is the unit of the concentration over the time. And here we need to remember that the unit of concentration, it is mole over decimeter cube. And for the time, according to the SI unit, it is the seconds. So from here, we can find that the unit is mole decimeter to the power of -3 second to the power of -1. According to the definition, we can find that if we want to follow the rate of the chemical reaction, we can either go within the change in the reactants or the products. So from here, I can read this following note. When measuring the rate of any reaction, we can follow the change in concentration of any reactant or product per unit of time. From here, I can go through the rule. Whenever I want to calculate the rate of the chemical reaction, I will be taking the change, and here, of course, we need to remember that the change is the delta. This is considered, of course, the change in the concentration of a product over time. If you look at the rule in this form, here I need to mention that any time in chemistry, if we put between brackets For example, let's consider HCl. The brackets here, it is for the concentration expression. Here I'm going to tell you that these brackets in chemistry, according to the IB syllabus, they are represented in more than one chapter. If you go back, you're going to remember that in chapter 2, we can use the between brackets and we can put the noble gas electronic configuration. So in this situation, the brackets, it is for the electronic configuration of argon. We also consider the brackets before in chapter 13, which is for the transition metals. We can put between brackets a complex ion. So I can also find these brackets in chemistry for chapter number 13, transition metals. And for our lesson today, we can also consider the brackets as being concentration. So this is also concentration. So the concentration change of the products over the change in time in seconds. And if we want to go through the rule another time, we can also follow the change in the concentration of reactants per unit of time. Here there is something so important as a difference between both rules. If you look at the rule, which is the second one, you're going to find that there is a negative presented beside the rate law. For what reason is this negative? This negative is so essential and important anytime you have a change in reactant. I'm going now to explain why. Suppose that you have a chemical reaction between magnesium and between hydrochloric acid. According to this chemical reaction, concentration 1 for the reactants, it was 2 mole per decimeter cube. So I've started with 2 molarity. Now, the big question, what happens to the concentration of reactant per unit of time? You can start thinking about this answer. Of course, if you are considering the reactant, so the concentration, which is C2, should definitely decrease as the reactants will be consumed during the reaction. So let's, for example, say that the concentration becomes 1.5 after a certain period of time. If I want to calculate delta, the change in concentration, according to the rule, it is C2 minus C1. The C2 according to my experiment is 1.5 minus 2. If you subtract, you're going to find that there is a negative sign that will appear. Here, in order to overcome this negative from my change in concentration, it is so important to multiply by a negative outside. So actually, this negative, which is presented, it is to overcome the negative sign formed from the change in the concentration of reactants. Here we need to remember something very important. Anytime we want to determine the rate of reaction, it is so important to have the final answer as a positive sign. So this negative is important if we are dealing with a change in the concentration of reactants. since the concentration of reactants decreases within time. Here I have a small example. Mg as a solid reacts with hydrochloric acid, aqueous, to form magnesium chloride as a salt besides the production of hydrogen gas. If I want to follow the concentration change per unit of time, so I can follow the concentration of hydrochloric acid as a reactant, and I also can follow the concentration change of magnesium chloride. When talking about concentration, so definitely I need to remember the use of aqueous as a state. So according to my balanced equation right here, I cannot follow the concentration of magnesium since it's a solid. I cannot also follow the change in concentration of hydrogen since it's a gas. So I have another and other experimental methods that can be used to monitor the chemical rate of reaction, and this is what we're going to discuss later. So according to this example, if you want to go through the change in concentration per unit of time, so you will be only focusing on the hydrochloric acid or the magnesium chloride. In this situation, since you are going through the rate of reactant, so you need to write a negative right here, and here the sign, it will be a positive. So if you are following reactants, you need to have negative sign, and if you have a positive, you have it's for the products. And according to what's given inside this is small box, the brackets are used to express the concentration, and we considered this before. So here I have the small note presented. So we need to make sure that this note is understood. The minus sign for the reactants is necessarily as the concentration of reactants decreases within time. But if we are following the concentration of product, it will increase. And we need always to remember that if we have a rate of chemical reaction, it should be always and always positive in sign. I've got here a small practice question for the calculations part. Question 1. The rate of reaction between hydrogen peroxide and iodide ions was measured by monitoring the concentration change of iodine. If 0.05 mole per decimeter of iodine is produced in the first 2 minutes. So iodine, it's my product. According to the question, I have 0.05 mole of iodine is produced within the first 2 minutes. And I want to determine the rate in a unit of mole per decimeter cube second. So in order to determine my rate, I'm going to put the change in the concentration of iodine per unit of time. And since this is a product, so no need to add the negative sign. According to the question, they gave me the amount which is produced, so I'm going to put it as a change in my concentration. Definitely, initially as iodine, I don't have anything, it was 0, so this was formed after 2 minutes, which should be converted into seconds. So for the 2, remember to convert to seconds. And the reason for converting is the unit. I need it in second. So 2 times 60, when you convert, using your calculator, your final answer is 4.17 times 10 to the power of negative 5 mole over decimeter cube and second. Now continuing with the P part of the question, what is the rate at which hydrogen peroxide is consumed? So now I'm going to find the rate with respect to another reagent presented inside my balanced equation, which is the hydrogen peroxide. Now we're going to learn something. The coefficients or the mole number are very important when comparing the rate of the chemical reaction. Since the hydrogen peroxide coefficient is 1 in the balanced equation, and the iodine, it is another 1. So as if you want to do a mole ratio. So the rate of the hydrogen peroxide consumed, it will be the same as the rate of the production of iodine. So for I, the rate of H2O2 will be the same as 4.17 times 10 to the power of negative 5. Now the question is telling me also to explain. So I will refer to the coefficient as a mole ratio. So I'm going to say because the hydrogen peroxide mole coefficient is the same as iodine. So if they have the same coefficients, we need always to make sure that they have the same rate. But if they have different, so we can apply on a mole ratio as in double I. In double I, it's asking me about the rate with respect to iodide ion. Where is my iodide ion now? So now my iodide ion, it is I negative. Going back to the question, we're going now to compare the coefficients. So this is my iodide ion. I'm comparing it another time with the iodine. So you can find that the mole ratio is 2 to 1. So if the rate of the iodine, it was 4.17 times 10 to the power of negative 5, this would be my X or my question mark. So how can we determine now the rate? So the rate of iodide ion, it will be twice, so 2 times 4.17 times 10 to the power of negative 5. Using your calculator, you can obtain your final answer. So from this practice, we need to remember that the coefficients are very important when comparing the rate of reaction. So I can write it as a note here to remember it. The coefficients are important for comparing the rate of reaction. So keep this note inside your mind. Now we're going to continue with more examples. I have now question number 2. Iodate ions oxidize iodide ions in acidic solution to form iodine and water according to the equation. If the number of moles of each reactant consumed after 1 minute was measured, which would have consumed been least? If the question is asking me for the least, so I need to refer it to the coefficients. So going back to the question, I will compare. I have the iodate, I have the iodide ion, and I have the hydrogen ion. Looking for the coefficients, the smaller coefficient is in case of iodate ion, since I have 1 mole, so it will be the least consumed. Continuing with question number 3, which statement is correct for the reaction of 4P plus Q to form 2P plus 2S? The rate of formation of R is 1/2 the rate of disappearance of Q. So here I'm comparing my R to the Q. Looking at the R, I'm going to find that I have 2 mole. So actually the R is faster by double, so this is incorrect. Continuing with B, the rate of disappearance of Q is 1/4 of the rate of disappearance of P. So now we are comparing the P and the Q together. Since the P is 4 as a coefficient, it is 4 times larger in rate compared with the Q. So definitely the Q is 1/4. This is a correct statement. If you're going to continue with C and D, you're going to find easily that both of them are incorrect. For the C, the rate of formation of R and S are not equal. They are actually equal since they have the same coefficient exactly. Compare, they have 2 and 2, so the same rate. And for the D, the rate of formation of S is double the rate of disappearance of the P. Actually, the P is the double than the S comparing the coefficients. Now we're going to a second important thing in section 6.1, which is the experimental measurement methods that can be used in order to monitor the rate of chemical reaction. We previously said that the rate of reaction can be followed by following the change in concentration per unit of time of either reactants or products. If we want to consider the concentration change inside the lab, it's not easy at all to follow the concentration. Since the experimental method, it will be not easy. So we have another and more than one experimental method to monitor the rate of the chemical reaction. If I want to monitor and to follow the change, I need to look for a property that I can follow it within time. I have here more than one property, so I have more than one method. We're going through the methods that can be used. Starting with the first method, I can use the change in pH per unit of time. The change in pH can be used anytime we have acid-base chemical reactions. How can we know that the reaction is acid-base? I have two essential ions if presented, so I have acid-base. It's the H positive, which is indication of having an acid, and I have the hydroxide, which is another indication of having a base. Here, since this is kinetic and till now we didn't go through chapter number 8 acid bases, but I'm sure that after completing acid-base reactions, you will be familiar on different types of acids and bases, and you will easily identify the presence of them inside any solution. The second experimental method that can be used, it is the change in conductivity. When can I use conductivity? It is when the chemical reaction involves electrolytes. What's the meaning of electrolytes? Electrolytes are solutions that conduct electricity. The question is why they do conduct electricity? Because they present ions. So if there are ions another time inside my balanced chemical equation, so I can follow the change in the conductivity. The third method, it is the change in the mass. Usually, the change in mass is used whenever you have solids and there is a production of carbon dioxide. We will look for an example later. Number 4, we have the change in volume. If you want to follow the change in volume, so the chemical reaction should produce a type of gas. This gas can be collected by different methods. We will also look at these different methods later. Number 5, you can go through the change in pressure. Usually the change in pressure is used for the chemical reactions that involve the presence of gases. So there will be a change in the pressure as a mole number. I have number 6, which is the change in color. When talking about the change in color, so here I need to start thinking, how can I know that the change in color could be a good method in order to follow the chemical reaction? If the chemical reaction presents a transition metal, and all transition metals, we considered them before in chapter number 13, they are colored. We have some exceptions if it's for the zinc, for example, but if it's a transition metal, their complexes and compounds, they are colored actually. And we have another 2 types of halogens. The presence of them will help you to remember that yes, if they are represented, I can go through the change in color. If you also remember in chapter number 2, the iodine and iodide ion, I can go through the color change. This is reddish brown. And the iodide ion, it is considered as being colorless. So there will be a change in the intensity of color. and you can follow in this situation the change in color. You can also go through the bromine that turns into I negative, Br negative. This one is orange, and it will turn into colorless. Now, the important thing that I want to mention here about the colors, I have here a very important note that will help you as a study tip inside your past paper. We have a type of gas, which is actually a colored gas, nitrogen dioxide, which is NO2. If NO2 is a presence inside the balanced chemical equation, you can use the change in color. And I have here a small figure that will help you to remember that NO2 is considered a colored gas. The color of this gas, it is orange, reddish orange color. So remember that the NO2 presence could be a change in color. All other types of gases, nitrogen, oxygen, noble gases, they are normally colorless. So you cannot go through the change in color. But the NO2 specifically, it is colored. The second thing that we need to remember here, what is the device that can be used in order to measure the change in color? It is called by colorimeter, from the word of color. And we have a special device called by spectrophotometer that might help in detecting the color change through readings of absorbance per unit of time. Now we've got a question. We're going to see how to apply on the experimental method that we considered before. For each of the following reactions, suggest a way in which the rate of reaction would be measured, followed, monitored experimentally, and explain your answer. So inside A, if you look at it, you're going to find that calcium carbonate, hydrochloric acid reacts to form calcium chloride, water, and carbon dioxide. I have here several methods that can be suitable. I can go through the follow a change in volume. Why can I use the change in volume? You've got carbon dioxide. Remember that the change in volume, the most important thing is to have a gas as a product. You can also go through change in pressure. Why is that? If you look at the reactants, you're going to find that we have 0 mole of gas. And if you look at the products, you will have 1 mole of gas. So since there is a change in the mole number of the gas, so of course, if you've got a pressure sensor, there will be a difference in the readings. So yes, you can also follow the change in pressure. You can go through also the mass versus time. Why the mass? As I told you previously, we have a solid and we have carbon dioxide, which is produced. So yes, you can go through the mass versus time, and all of that, all of these different methods can be used because of having carbon dioxide. Now I have the B. Hydrogen peroxide plus 2 iodide ion, 2H positive to form iodine and H2O. Here I have several ways that can be also used to monitor experimentally the rate of production of iodine or the consuming of hydrogen peroxide. First way, which is number 1. You can follow conductivity. Why? If you remember, conductivity is the presence of ions. So if you look at, you're going to find that we have a decrease in the amount of moles of ions comparing the reactants to products. So I have 2 I negatives, I have hydrogen ion as well. Looking at the product, I don't have any ions. So here the conductivity will decrease. Remember that whenever you want to explain, you need to go through a decrease or increase in the property while answering according to the past papers. Number 2, you can follow the change in pH per unit of time. Talking about pH, so I'm talking about hydrogen ions. So if you look at the balanced chemical equations, you have 2 moles of hydrogen ions. So another time, there is a decrease in the concentration of hydrogen ions. So there will be a change in pH. So yes, you can use this method. Number 3, you can follow the change in color per unit of time. Why can we use it? I've got iodine right here. So the color will change from colorless, which is for the iodide negative, into reddish brown, which is due to the formation of iodine. Remember another time, as a small note, for any change in color, it is better to specify the color change when you want to outline or to explain, giving a reason. Many of the past paper questions may ask you to give a suitable experimental method without writing the explanation for it or without outlining. So be careful in reading the questions carefully. Continuing with C, magnesium plus hydrochloric acid produces magnesium chloride and hydrogen gas. There is a gas, so of course I can go through the change in volume. I can collect the volume of hydrogen. I can also go through the pressure. I have here 0 mole of gas and it turns another time into 1 mole. So yes, I can go through the pressure versus time due to the production of H2. Can I ask about, is there any other method that can be used for this C example? Is there here an acid? Yes, there is. So you can also follow change in pH with time. So yes, we can add. Can I use a color? Of course, no. I don't have a transition metal. I don't have an iodine or bromine. I don't have a change in color here. I cannot go through the colorimeter. Continuing with D, NO plus O2 to form NO2. Here you can follow the change in volume or pressure versus time due to the production of NO2. Here there is one thing which is so important to consider. Why the pressure is a suitable way for this example. We will make a small comparison based on the total mole number. So I have as a reactant 2 and 1, I have a 3 mole of gas. Compared with the products, I have 2. So since I have a change in the mole of a pressure, so yes, I can use the change in pressure versus time. So here I need to remember that the pressure mole of gas should change. This is so important. If the mole of gas didn't change, as for example, you have 2 moles of gas as reactants and another 2 moles of gas as a product, so in this situation, you cannot use the pressure versus time. Can you use in this example the colorimeter? Yes, I can. So you can also go through the colorimeter, which is the change in color per unit of time. Now for the E, MnO4 negative, 8H positive, 5Fe positive 2 to form manganese positive 2 for water molecule and the iron. I can of course follow the change in conductivity. You need to consider what happens to the amount of ions. So you can say that the amount of ions got a changing here. So yes, there is a change in the amount of ions, so I can use the conductivity. I have another method as well. I can go to the follow of change in pH. I have H positive. If you look, H positive as a reactant, it turns into nothing as a product. So there is a decrease in the concentration of hydrogen ions. Finally, I can go through the change in color per unit of time. I've got in this situation the permanganate, which is considered purple, turns into colorless. There are a lot of transition metals which are colored. Maybe you will start asking, what about the transition metals? What colors I need to know? Do I need to know all the colors change? According to redox, I'm going to give you later in chapter number 9, some transition metals ions you need, yes, to memorize their name, and you need also to memorize their color change. For the kinetic chapter here, this is one of them, which is the permanganate ion or the manganate ion. The MnO4, when it turns into Mn positive 2, it actually changes from the purple color into the colorless. So you can keep this as a note. I've got here two multiple choices. I'm going to focus on the first one. The rate of chemical reaction can sometimes be determined by measuring the change in mass. Anytime, remember, if the question is telling you change in mass, remember that you need a solid as a reactant, and you need a production of gas, which is usually CO2 gas. This should be very important, understood before going through the options. For which of the following reactions would this technique be most successful? So we will start now looking for which one of these options consider the solid as a reactant and there is a production of carbon dioxide. You're going to find that the answer, it's a C answer. Remember that copper carbonate and dilute hydrochloric acid, so I'm talking about copper carbonate plus hydrochloric acid, when they react together, they will produce for me the salt, copper chloride, plus water, besides the production of CO2. Where's my solid? This is my solid, which is the copper carbonate, and it will react with the acid. So the answer is C. You wish to carry out an investigation that involves the use of conductivity. So conductivity, I need to have a change in the ions as mole number. So start thinking, which one is the correct answer? To monitor the rate, which of the reaction below would be the least suitable for that? Least suitable, so we do not have ions at all. Which one do not involve a change in the ions? It's the D answer. And all of the above A and B and C, you can find here that there is a decrease in the ions, there is a decrease in ions, here there is an increase in the amount of ions, so definitely the change in conductivity could be used. Now the last question related to this idea, for which of the following reactions would a colorimeter be suitable for monitoring the reaction? Colorimeter, so it's the change in color. Start looking for which of the options contains a transition metal or iodine besides having bromine. You're going to find that the A is the correct answer. The reaction of acidified permanganate. So I've got here permanganate ion. This is the manganese. So there is a color change. We will go through a little bit the experimental methods that can be used. I'm going to start with one of the most important experimental methods that we used inside the lab, which is in determining the change in volume per unit of time. If you want to go to the lab and you want to apply on the change in volume, so what are the possible two different experiments that can be used? To collect the gas produced from a chemical reaction, two experimental methods can be used. The first one is the gas syringe. The second one, it is called by the inverted graduated cylinder. Let's look at the figure. If you look at the first, this is for the gas syringe. Okay, what can you see according to the equipment and materials needed? Definitely I need a flask. I'm going to put my solid, which is in this case the magnesium. I added the hydrochloric acid in a specific volume and concentration. So I have my conical flask. It is connected by a rubber band. And we have, of course, a glass tube as a delivery tube. We have a rubber connector, and we have here the gas syringe. Now, what will happen? The chemical reaction produces hydrogen gas. So definitely, it will start to go into the gas syringe. So what will happen to the plunger? It will be pushed. So if I'm going to talk about little bit the data collection here, what data you're going to have? Firstly, you need a stopwatch. So I have a time and I will be taking the volume of hydrogen gas, so the volume readings, and cubic centimeter. You will start from the 0 and maybe each a specific period of time, let's say 30, 60, 90, and 120. So you will have your stopwatch beside you, and you need to start taking now the volume readings. So initially, at the beginning of the reaction, of course, this would be a 0. Within time, the volume collected will increase. Let's suppose that you have 2 cubic centimeter here, then increases to 5, then becomes an 8, then it becomes constant. Why do you think it becomes constant? The volume becomes constant. This is an indication that the reaction reaches completion. So the reaction is ended. Reaction is ended. So this is how can you know that the reaction is already done. So if you want to take your data and you want to draw the relationship here, so you will be taking the y and the x, and this is what we're going to talk about in our second part of our lesson. So we will have here the volume and we have the time here. So we will have a shape of graph like that looks like this. Then it becomes constant, indicating that the chemical reaction reaches completion. This is for the first experimental method, which is the gas syringe. Continuing with the second, which is the inverted graduated cylinder. You're going to find that you have also a conical flask, and inside the conical flask here, I have a reacting solid. You can take it as the same solid. For example, if you've got Mg, and you added the hydrochloric acid as well, which is the same as previous. Now you're going to connect by a delivery tube into a trough, which is filled with water. Now the measuring graduated cylinder here, I have a specific volume as an initial volume. Let's say it was a 90 cubic centimeter. So the graduated cylinder is actually inverted and the water is presented inside. So another time, what will happen inside my second experiment? What are my data? I will have the time, and I will have, in this situation, the volume of water, since I'm going to collect water. Oh, I'm going to read, the water level. So I have here 0, 30, 60, 90, and 120. The initial volume of water inside the inverted graduated cylinder is 90. As mentioned earlier, it will be filled with a specific volume. Now the question, what happens to the volume of water per unit of time when the chemical reaction started? Hydrogen gas, which is produced from the chemical reaction, will be collected through the delivery tube into the inverted graduated cylinder. Now what will happen? The gas, it has a low water solubility. So it will start to fill inside this empty space and it will push the water level down. So within time, we're going to find that the volume of water will decrease. So suppose that it becomes 88, then it becomes an 85, then it becomes an 83, then it's now constant. So another time, the chemical reaction reaches completion at 90, so ended. So this is the total time taken for the reaction to end. If we want to go through the graph, so we can draw the relationship between the volume of water and we have the time. In this situation, the shape of my graph, it will be a decreasing within time, then it will become constant like this. You can also have another graph which shows the relationship between the volume of the gas that has been collected, which is volume of hydrogen gas, and here I have the time. But I need to start thinking, how can I have the volume of hydrogen gas instead of the volume of water? So I need to have another table that shows the relationship between the time and between the volume of H2 gas. I have 0, 30, 60, 90, and 120. Initially, the volume of hydrogen gas collected is 0. Now the question is, how can we fill inside the table? We need to refer to the previous one. What we're going now to do, we're going now to subtract in order to find the volume of hydrogen. So if we subtract 90 minus 88, it will be 2 cubic centimeter. You will also subtract 90 minus 85, so it will be 5 cubic centimeter. So each time you need to subtract from the original. Now you have 90 minus 83, which is equal to 8 cubic centimeter. Sorry, it's a 7 cubic centimeter. So now I have my values. I have 2, 5, 7, then it becomes another 7 as the chemical reaction reaches completion. Now you're going to draw the relationship between the volume of hydrogen and between the time. So it will be increasing, then it becomes straight constant as the chemical reaction is ended. So these are the two different methods that can be used in order to collect volume. Either the gas syringe experiment, or you can go through the inverted graduated cylinder. From the past paper, actually from paper number 3, they may ask you about some possible systematic errors when we're going to apply on the gas syringe experiment. So these are the possible answers. One of the systematic error is the gas may leak, be lost, escape. Definitely, it may leak. And as you can see here, I have rubber connector. I have from also the rubber band right here. There is a possibility also for the gas to leak from here. So this is a systematic error. Another one, the plunger may stick friction. Inside the plunger, maybe there is a friction, so the hydrogen gas will not be able, or the carbon dioxide or any type of gas cannot be able to push the plunger. Number 3, the syringe may be tilted up, so the plunger moves less. If we go back to the figure, we're going to find that my gas syringe should be exactly parallel with the bench. When you're going to connect the gas syringe, you need to make sure using the clamp and the stand to be secure, and it should be parallel to your bench, so not to be tilted. Of course, if it's tilted up, which is something like this, what will happen? The plunger in this situation, it will not easily move. The number 4 now, gas may dissolve inside water. Here, this is another expected possible systematic error. I suppose that the gas to insert into the delivery tube, maybe the gas that has been formed according to my experiment, it will not follow to reach the gas syringe. So it can easily dissolve instead of being collected. So this is another systematic error. For all these errors, whenever we want to study chapter number 11, we need to make sure that we know the direction into which the error is affecting. For all errors above, the volume of gas that will be collected, it will be smaller than actual. And how can this affect my rate of chemical reaction? So definitely you're going to have smaller rate of reaction than actual. I have here another following experimental method, which is the change in mass within time. Usually, the change in mass is used whenever you have a chemical reaction between calcium carbonate. This is a very common chemical reaction used in the past paper. Beside the addition of an acid, when it forms, it will give me the calcium chloride beside the H2O, and you have the CO2. Here I have the solid, and I have the carbon dioxide gas. So if we look at the chemical reaction setting up, what do we have? We have the flask. Inside the flask, we have marble chips. When talking about marble chips, this is the calcium carbonate actually. And according to this experiment, it was with a 20 gram of marble chips. And I have the hydrochloric acid with a specific concentration added. Now what happens? You've got a digital balance and you have here an initial reading. Suppose that the reading of your balance, it was, for example, 80 gram. So I started with 80. So if I'm going to have now my data, I'm going to have here the time. And here I have the mass of a flask plus its content. So initially the time at 0, the mass, it was 80. So you need to add the hydrochloric acid or the marble chips to each other, then to start your stopwatch immediately and start to take readings each specific period of time. So now the question, what happens to the mass of a flask and content? According to my chemical reaction, I have carbon dioxide that will be formed. So now the carbon dioxide will go through. It can easily go through the cotton wool presented and it will escape outside. So the mass of the flask will decrease. So it will become smaller and smaller. So suppose that the number comes here into 70, let's say 5. Then it decreased into 73. Then it becomes 70. And another time it becomes a constant 70. So this is an indication that the chemical reaction reaches completion. So if I'm going now to have a graph, of course, the relationship, it will be between the time. So I have here my time. And I have here the mass of the flask. It's decreasing, so it will start to decrease like this, then it becomes constant. Now, can you draw another graph? Yes, and somehow this is so similar to the inverted graduated cylinder, since you can be more specific and you can put the mass of CO2 and you can put here the time. The graph, it will be an increasing per unit of time and it will become constant. From where the mass is, as I told you previously, you're going also to subtract 80 minus 75, so it's a 5 gram. Then 80 minus 73, so it's a 7 gram. And here it is a 10 grams and another 10. So the mass of CO2, it's actually increasing as a product per unit of time. I have here, so 2 small notes. The mass of the flask and its content decreases within time as the carbon dioxide gas escapes out of the flask. Now, why do we close the flask using a cotton wool? This will allow the CO2 gas to escape, but it prevents splashing of the liquid. I have now another important experiment, and this experiment is one of the questions that are usually presented in the past paper. You can find several questions related to this one, and we will apply on this idea later after finishing Kinetics. The reaction between hydrochloric acid and sodium thiosulfate. What is hydrochloric acid? It's the HCl. What is sodium thiosulfate? It is the Na2S2O3. Here I have the chemical reaction. So we will be adding sodium thiosulfate to the hydrochloric acid. I will let you see what is taking place. Look at the diagram, the figure which is presented right here. Inside the flask, according to the experiment, you're going to bring a piece of paper. And there will be a cross. Both solutions which are presented inside the flask, the HCl and the sodium thiosulfate, They are at the beginning of the experiment colorless. Let's see now the chemical reaction. Sodium thiosulfate and hydrochloric acid, they react together to form NaCl. There will be a production of the sulfur solid, and there is carbon dioxide, and we have H2O liquid. The sulfur, it's a yellow color, and this is a gas that will be produced beside having the water. So can you start thinking what will happen to the cross within time? Since this solid is yellow and I have sulfur dioxide formed, so this is actually what will happen. Within time, the color starts to change. So the solution color changes. It actually turns into yellow color, turbid yellow color. Why is this yellow? Due to the sulfur. Beside having the SO2 gas that will be formed, it will also help in diffusing the color throughout all the container. So let's go back another time to the first point mentioned inside the slide. Sodium thiosulfate reacts with hydrochloric acid to give a reaction mixture that gets more cloudy as yellow solid sulfur is formed. Inside the past paper, one of the questions was to complete the equation, and they ask about the water actually as a production beside writing the state. So the equation is important. They asked about the water and the state of it as completing. How can we monitor the rate of the chemical reaction? What we're going to measure here. For this reaction, we need to measure using a stopwatch the time taken to be unable to see the x-cross drawn on the paper sheet. So you will start looking at the flask and you will have your stopwatch beside you and you will start measuring the time. So I'm going to add both liquids together, HCl and sodium thiosulfate. Immediately I will open up my stopwatch and I will wait. I will look at the container above, and when I'm not able to see the x-cross, this is an indication that the chemical reaction is ended. So you need to stop this stopwatch. So what is the only measurement data collection reading do I have? I'm measuring the time. This is the only thing that I have. It's the time till the cross X disappears. So how can I determine the rate of the chemical reaction? The rate of reaction in this situation, it will be 1 over the time. And please remember this rule. It's so important. We will apply on it later in the past paper. So what would be the unit of rate? It will be second to the power of -1. So from here, remember that if a chemical reaction occupies only a time, you're going to calculate the rate by having 1 over the time, which in this situation will be second to the power of -1. Another thing that you need to take it into consideration here, this chemical reaction usually takes place in fume hood. Fume hood. It is a place which is so important for the chemical reaction to take place inside. Now, when talking about fume hood, it is the place that can take the unpleasant and toxic gases that would be produced from the chemical reaction. Why? For what reason do we need to use the fume hood? You need to know that the sulfur dioxide, the sulfur produced, they are actually toxic. We have unpleasant smell that will be formed. So keep this inside your mind. Toxic. Okay. Now we're going to continue with the rate equation. We have something called by the rate equation. We're going to start with it now. I've got here a balanced chemical reaction that shows the reaction between A and B to form C and D. If you remember, according to our definition for the chemical rate of reaction, the rate of a chemical reaction, it can be followed by the change in the concentration of any reactant or product. So I can go through the change in the concentration of A per unit of time. I can go through the change in the concentration of B as a reactant per unit of time. I can continue with the rate of C as a product per unit of time, or the change in the D. Okay, I'm going only to exchange it. This is the D. Okay, in this situation, you can find that the negative, it is presented in case of reactants, and we took this before. What is the rate equation? The rate equation, it's an equation that we can use in order to compare the rate of each reactant or a product by the one another. How can we write this rate equation? It's presented right here. Okay, what can we see? We're going to take the coefficient, so 1 over the coefficient of A, delta, concentration of A over delta T, and I've got here a negative, equals negative 1 over the coefficient of the B over the change in concentration of B over T, and 1 over the C, the change in the C over delta T, and finally I have 1 over the D, a change in concentration of D over delta T. If you look at this relationship between one rate of chemical reaction and another, this is called the rate equation. We are using it in order for the comparison part. So as if we want to compare the rate of the first reactant to the second, to the products, and so on. How can we apply on this idea? I've got here a past paper question. The question is, the equation for a reaction is 4NO2 plus 2H2O plus O2 to form 4HNO3. Which one of the following is not numerically equal to the others? They are trying to ask me here about the rate equation. The first thing, if you look at the numbers given in A, B, C, and D, let's start with the A. Concentration of N2 over delta T. What is the coefficient here? According to my rule, it's the 2. Let's go back. I've got here a 4, so there's a problem. Considering also B, what's the coefficient of 2 according to the options? It's a 2. Look at the coefficient, it's a 1. So there is something here before starting thinking about the answer. Actually, there's an idea here. Before starting looking for the answer, I need to think about what happens to the equation. Actually, the equation was firstly divided over 2. So it was NO2 plus 1 mole of water molecule plus half O2 to form my 2HNO3. So the first thing is to rewrite the equation after dividing over 2. I think about that since if I started reading the answers, we're going to find that all of them, they are incorrect. So there is a case here. Now, after dividing by 2, I will start by looking where is my incorrect answer. So starting with A, is it minus 1 over the coefficient? Yes, it's right. So this is the correct answer. Continuing with the oxygen now, it is negative 1 over 2. Okay, let's go through the rule. The rule says it's 1 over the coefficient. 1 over the coefficient. Delta concentration of O2 over delta T. Let's apply. So it's 1 over. What's the coefficient of oxygen? It's a half. Delta, the concentration of O2 over delta T. So if you want to rewrite it, it will become a negative 2 delta concentration of O2 over delta T. So this is my correct answer. Here I have a problem, so this is incorrect, and the B is not numerically equal to the others. I've got now the graphs that are usually used in order to determine the rate of a chemical reaction. We have actually two types of shapes, or I've got two types of graphs according to what I am following per unit of time. If you are following reactant property, so you're going to have here the property which is for a reactant. No matter what is this property, could be a pH, could be a conductivity, could be a volume, could be a mass, could be a concentration, and you have here a time. So now we need to start thinking, what happens to this property as I am considering a reactant? So I need to remember that it will decrease per unit of time, then it will become constant. So when the line becomes constant, exactly at this time, I'm going to consider that the reaction is completed. So here, ended. So this is the time at which the reaction is completed exactly. Now, if you are considering a property which is for a product, so on the y-axis, you have the property which is for products. And I have the time. This property could be anything: mass, volume, pH, conductivity, concentration. What will happen? Start thinking. Products, at the beginning of the reaction, it's a 0. Then it will start to increase. Then it will become constant. When it becomes constant, this is an indication that the reaction reaches completion. It ended. So the reaction ended. These are the two shapes. These are the two graphs. We're going to learn later how can we use these graphs in order to determine the rate of a chemical reaction. Looking at the graph which is presented at the bottom, this graph shows if you are following the concentration per unit of time. And here both curves are joined. So I have the products that will start with 0 and increase. And I have the reactants that starts with a higher concentration and decreases per unit of time. This is where both of them, the curves becomes constant. So if they ask you as a question, outline, state why the curves at the end of the chemical reaction becomes constant, this is an indication that the chemical reaction is completed. The reaction reaches completion. So this is the time. And both of them, they will have the same ending, no matter you are following reactants or you are following a products. I'm going now to stop for my lesson for today. Next time for the kinetic, we're going to learn as a standard level also, how can we use these two graphs in order to determine the rate of chemical reaction. We have actually 3 types of chemical reactions: the average rate, the instantaneous rate of reaction, besides having the initial rate of reaction. This would be our lesson next time.